Here the statement of the problem is a parallel beam of light composed of a red and a green light ray is incident obliquely at a point on the face of a rectangular slab. When coming out from the opposite parallel face, the red and the green light rays are emerging, and there are four options. They are being non-parallel and separating to each other. They are being parallel to each other. These statements are regarding the emergent rays, right? While the information regarding the incident rays are given to you, the informations. And one more thing is given to you, that they are being incident on a parallel slab, parallel rectangular slab, right? Rectangular slab, where the faces are parallel. What happens when a ray is incident on a rectangular slab where the two faces are parallel? They got something which we know as lateral shifting, right? You must have studied the formulas for lateral shifting. Okay, let's look into the figure. This is a rectangular slab, if you can see, and the rays of different colors are being incident onto it obliquely at the same incident angle, at the same angle of incident for different colors, right? Color 1, color 2, and what is the angle? Let's say this is I, right? For both of them, I, which is not equal to 0, that what it means by oblique incidence, right? With respect to normal, so they are being incident. Now if we focus on to one particular ray, what happens? Because this glass slab is a denser medium, optically denser medium, what happens? The ray which get refracted on the first phase, it gets bent towards the normal, right? Let's say it makes an angle R, correct? Now if you apply Snell's law on the first phase, what you get? You get mu air, that is 1, multiplied by sine I is equal to mu of glass into, what is this? Angle of refraction, R. So that's sine R. That's equation number 1. Let's say this is equation number 1. Let's say I'm talking about a particular color and this is my equation number 1 for the refraction on the first phase. Now this ray comes and it becomes the incident ray for the second phase. The refracted ray from the first phase becomes the incident ray onto the second phase, correct? And because the second phase is parallel to the first phase, what happens? Please look into it. This R is equal to this angle, right? So this is also R. Now this angle is the incident angle for the second phase. Why? Because this is incident ray now, and it is being incident onto the second phase, making an angle R with respect to normal. So this R becomes the incident angle of incidence for the second phase, correct? Let's say angle of emergence is E, and it is being emerging into the air again, right? So again you apply Snell's law for the second phase. For the second phase, when you apply Snell's law, what you get? Mu glass into sine of incident angle, that is R this time, is equal to mu air, that's 1, into sine of refraction, sine of angle of refraction, that's E. From equation 1 and 2, if you look, from equation 1 and from equation 2, if you look, I becomes equal to E, correct? That means in this case, this angle of incidence is same as final angle of emergence. This is happening because these two surfaces are parallel to each other. So whenever a ray is incident onto a slab whose two surfaces where the refraction is taking place are parallel, then the emergent ray, the final emergent ray, will be parallel to the incident ray. Why so? Because I becomes equal to E. So now you see this. If you take this like this, if you like extend the figure of the incident ray, then this is I, correct? And if you just do this, so if this is I, this total will be I, correct? And if this total is I, and you see this is E, so this total will be E, right? And I is equal to E. That means they are making same angles with respect to normal. correct? So that means this ray and this ray, the incident ray, the initial incident ray for a particular color and the final emergent ray for that particular color, they are parallel, they are being parallel. What is happening? There is a perpendicular shifting, right? This much. This we call lateral shift. The lateral shift you might have studied the formula for. You might have studied the derivation of the formula for the lateral shift for this distance d. Of course, the formula is not required in this particular case. We just need to discuss the theory. So we are not focusing on the formula. But one thing you should note down, that for this particular slab, the incident ray for any color and the emergent ray, they are being parallel. So if this is parallel to this, if this same way is parallel to this, and this ray and this ray, the two incident ray of two different colors, they are again parallel to each other. So that's why the emergent rays are also parallel to each other. So the rays which are being like which are emerging from the slab, from the second surface of the slab, for the two colors, they will be parallel to each other, correct? So the answer in this case will be parallel to each other, right? Let's look into the options. Option B will be the correct option in this case. Here the statement is, the length of a vertical pole at the surface of a lake of water, where mu of water is given to be 4/3, is 24 centimeter. Okay, first read out the problem, then I'll discuss the details. Then a fish just below the water surface, for a fish just below the water surface, the tip of the pole appears to be at. That means it is asking about the apparent height, of the tip of the pole for the fish. So a fish will be an observer and the tip of the pole will be the object, right, in this problem, and it is asking about the apparent height, right? So this is a problem related to the famous apparent height problem, right? Now in this apparent height problem, you might have learned the formula directly, you might have used it so many times, but let me discuss the details of the formulation once and for all, so that you don't get confused in different kind of problems related to the same concept, right? Okay, this is the problem statement. Here, what is d apparent that is being asked? D apparent means the apparent height of the pole, of the tip of the pole, as appeared by the fish, or like as it is appearing to the observer, which is fish in this case, right? So fish is an observer, agreed, and this pole is the object, agreed. Now object, if you see, is at a height 24 centimeter from the surface of the water, from the interface of the two medium, correct? So the actual height, the d real, that is given to be 24 centimeter. Now in these cases, all of these problems, we use one formula. Please look into it. We use the formula mu I. You might have studied different varieties or like different formats of writing down the formula. I am telling you one, see if it is easy for you, easy to remember. Mu I by mu R is equal to, first let me complete the formula, then let's explain the meaning, is equal to d real divided by d apparent. Sir, what is this? Explain the meaning. I will. What is mu I? Mu I is the refractive index of the medium where the incident rays are present. I'm not saying where the object is present. I'm saying where the incident rays are present. Because there might be a case of virtual object, right? So please remember what I'm saying. Mu I is the refractive index of the medium where the incident rays are present. Mu R is the refractive index of the medium where the refracted rays are present. In this case, if you see, the object is here in the air, right? In the air. So the object will, it's like the incident ray will emerge from the object like this. So the incident rays are present in air, correct? So the air will have mu I, which is equal to 1, correct? And because there is a refraction and the observer is in water, so the refracted rays are present in water. So where are the refracted rays? In water. So the refractive index of the medium where the refracted rays are present is equal to 4/3 as given. Correct? Mu I is the refractive index of the medium where incident rays are present. Mu R is the refractive index of the medium where refracted rays are present. And then you apply this formula. So mu I will be equal to 1. Mu R will be equal to 4/3. Will be equal to d real, the real height of the object, the real distance of the object from the interface. What is that? That is 24 centimeter, right? So this is 24 divided by d apparent. Can you figure out what is d apparent from there? Of course, sir. D apparent will be equal to 4/3 into 24. Correct? In centimeter, of course, because d real is given to be in centimeter. So d apparent comes out to be 32 centimeter. Am I correct? Yes, I am. So the answer to this problem will be the apparent height of the tip of the pole as observed by the fish will be 32 centimeter above the interface. 32 centimeter above the interface, not from the fish. It is above the interface, right? Okay. 32 centimeter above the water surface. Let's look into the options. Option D will be the correct option in this case. Here the statement is, the same color of light takes time t1 and t2 to travel the same distance x in the two different media A and B respectively, right? The refractive index of the medium A with respect to B will be, and then there are 4 options. Okay, what is being asked? The refractive index of medium A with respect to B, that is mu of A divided by mu of B. That is what the question is, right? You have to get the value of this. Okay, with respect to, or like with the help of the given data, and you have to mark one of the correct option. Which one is the correct option that you have to get? Okay, let's look into the details. These are 2 slabs of different media. Let's say this is A. Let's say this is B. Correct? And the light is incident on both of them, like this. Now, when it incidents on both of them, it takes different time interval to travel distance x. In the first slab, that is A, it takes t1 seconds. In the second slab, that is B, it takes t2 seconds. Why so? Sir, when the distance is same, why the time taken is different? The time taken is different because the speed of light ray inside different medium is different. Why, sir? Because mu of a medium, as you have studied, is given by C by V. What is C? C is the speed of light in the vacuum and V is the speed of light in the medium. So mu is proportional to 1 by V. That means higher the refractive index, lower will be the speed of the light ray in that particular medium. Correct? Now, with that information, mu proportional to 1 by V, can you say that mu of AB, which is mu A by mu B, will be equal to VB by VA? Because mu is proportional to 1 by V. It is inversely proportional to the speed of the light ray inside the medium. So the ratio of mu's will be the inverse ratio of the speeds of light ray in the medium, right? Now, you know one thing, but VB by VA is not the option. So like, had it been an option VB by VA, I might have ticked it. But then you have to relate it with certain other thing as well. What is the thing? In the first medium A, to travel the distance x, it takes t1 seconds. T1 seconds with the speed VA. Correct? So x, that is the distance, is equal to speed, which is VA, multiplied by t1. Can I say that? Of course, sir. No problem till now. What about this? X is equal to, here t2 seconds is being taken, but the speed in medium B is VB. Correct? So x is equal to VB into t2. When you put them equal, see, x on both the sides, it is x only, right? So what I can say is VA into t1 is equal to VB into t2. Correct? So VB by VA will be given as T1 by T2. And from the formulation, from the concept mu proportional to 1 by V, I know mu A by mu B is equal to VB by VA. So VB by VA is T1 by T2. So mu A by mu B will also be equal to T1 by T2. So what should the answer be? In this problem, the relative refractive index of medium A with respect to B, that is mu A by mu B, will be equal to T1 by T2, right? T1 by T2, option D will be the correct option in this case. This is one of the very important problems from the perspective of the examination and the understanding of Snell's law as well. This basically belongs to the vector form of Snell's law, which you might have studied in the theory. You might have missed studying that. But here we'll discuss it in details and we'll see how the Snell's law is transformed into vector equation, right? You must have done it in the theory sessions, right? Okay. Now, the question says, if I cap denotes the unit vector along the incident ray, R cap is a unit vector along the refracted ray into a medium of refractive index mu, and N cap is the unit vector normal to the boundary of the media, right, directed towards the incident medium. Then consider the first medium to be air. Which of the following relations is true? There are 4 relations. Basically, these are the 4 formats. These are the suggested formats for the vector form of Snell's law. Correct? We'll look into it, we'll look into detail, and we'll figure out which of the vector form is correct. Okay? Let's look into the figure. So this is the system given to you. This is maybe a medium, a slab is given to you, right? And the refraction is taking place. We are taking the first surface. The first surface, if you take, the incident ray is along the unit vector I cap. I cap means the magnitude will be unity, but it shows the direction of incident ray. This is R cap, the unit vector along the refracted ray, right? So the magnitude of I cap and R cap in this case will of course be unity, but they are just reflecting the directions of incident ray and the refracted ray, correct? Okay, and this is N cap, directed towards the incident medium, right? Okay, so let's say this is all in the plane of paper, right? Let's consider a perpendicular direction Z cap, a perpendicular vector Z cap, unit vector Z cap, which is coming out of the plane of paper. Can we do that? Of course we can do that, right? We are considering that Z cap. It will be helpful to deal with the vector form. Now, what is the general statement till now you have understood about the Snell's law? The Snell's law says mu1 sine of I is the incident, is the angle of incident, is equal to mu2 into, that is mu medium into sine of R. Correct? Where I is the angle of incidence and R is the angle of refraction. Correct? Now, I would like to transform this. But first wait. Let us calculate a few things which are important for the transformation. Let's look, what is the angle between I cap and N cap? Is it I? No, it is not. See, I cap is like this and N cap is like this. Please understand this. And this angle is I. So the angle between I cap and N cap will not be I. Do you understand why? Because when you measure the angle between two vectors, you should always draw them head to head or tail to tail. Correct? So if you extend this, if you parallelly displace this I cap, this is this. Then what is the angle between N cap and I cap? Are they now tail to tail? Yes. So the angle between I cap and N cap will be this. And what is the value of that? 180 minus I. Am I clear with that? Correct? Now, I ask you to calculate what is the value of I cap cross N cap. I cap cross N cap. The cross product of two unit vectors. That's magnitude of I, that's 1, into magnitude of I cap multiplied by magnitude of N cap, that's again 1, into sine of angle between them. Sine of angle between them is sine of 180 minus I, multiplied by the unit vector perpendicular to both of them in the cross manner. So in the cross manner, if you extend your fingers towards I cap and you curl it towards n cap, then you get the direction of z cap. Correct? I cap cross n cap. Curl it like this, then the thumb will point outward normal, towards the outward normal. So it is z cap. Correct? So I cap cross n cap will be equal to sine 180 minus theta is sine theta times z cap. Let's say this is equation number 1. So this is equation number 2. Correct? Now let's calculate the similar thing for r cap and n cap. See, r cap is like this from this phase boundary and n cap is like this. Correct? And this angle is given to be r. Then what is the angle between r cap and n cap? Is this r? No, it is not. It is this angle. Correct? And what is that? That is 180 minus r. So what is the value of r cap cross n cap? Okay, r cap cross n cap. What is the value of r cap cross n cap? That will be mod of r into mod of n, that is 1 into 1 because they are unit vectors, multiplied by sine of angle between them, sine of 180 minus r, and then again the unit vector multiplied by the unit vector in the cross manner. Cross manner means r cap cross n cap. If you curl the fingers from r cap towards the n cap for the right hand, right, your thumb will direct upwards again, so it's z cap. Correct? So this becomes r cap cross n cap is equal to, please understand this, sine of r times z cap. Equation 3. Now look at equation 1. There are two things which are being equal. Can we multiply both the sides by z cap? Yes, we can do that, right? To transform into vector form. So mu1 sine I times z cap is equal to mu2 sine r times z cap. And sine I times z cap is I cap cross n cap, correct? From the equation 2. And sine r into z cap is sine r multiplied by z cap is r cap cross n cap, right? So we will just remove sine I times z cap and sine r times z cap by I cross n cap, I cap cross n cap and r cap cross n cap, right? So what we'll get is mu1 sine I z cap. Sine I z cap is I cap cross n cap is equal to mu2 multiplied by sine r times z cap. That becomes r cap cross n cap. Correct? Okay? Agreed? Now mu1 is 1 because simply the statement given is take the outer medium or the medium of incident, like medium where the incident ray is present, to be air. So for air it is 1. So it becomes I cap cross n cap is equal to mu times. Mu is the refractive index of the second medium. So mu times r cap cross n cap. That will be the correct vector law form of the Snell's law in this case. Let's look into the answer. Is that same? I cap cross n cap is equal to mu times r cap cross n cap? Yes, it is. Let's look into the options. Option C will be the correct option in this case. Here the statement is, a ray of light travels in the fashion as shown below in the figure. I'll let you see the figure. Wait. After passing through the water, the ray grazes along the water-air interface. Grazes means it escapes parallel to the interface. I'll let you see in the figure. The value of mu g in terms of I. Okay. You have to figure out what is the value of mu of glass, right? This is the system shown to you. The light ray, it is first coming from somewhere, getting refracted onto glass water interface, and then it is traveling in the water, and then it is getting refracted onto water air interface. Water air interface. This is air. Correct? And it grazes along the water surface. That means it escapes in the air parallel to the water surface. Correct? So this is the normal, let's say, normal let's say small n, then it grazes along the water surface means it escapes parallel to the interface. Please remember this. Many times they use this word, grazes. Grazes along the water surface means it escapes parallel to the water surface, correct? Now if we look into the detailed picture, let's say for the first interface, the initial incident angle is I for the first refraction and the angle of refraction is R. Then because this is a normal n cap and this is also the normal n cap to the parallel surfaces, then of course this normal and this normal, they will be parallel, right? Because this surface and this surface, they are parallel, correct? So for the second refraction, if you see in between water and air, this R will be equal to this R, and this now for the second interface is the incident ray. So for the second surface, the incident angle is R and the escape, the angle of escape E is given to be 90 degree. Why 90 degree? Because it grazes along the water surface, right? So it goes parallel to the surface. So with respect to normal, the final emergent ray will make an angle 90 degrees. Agreed till the point? Okay. Now for the first interface, if we apply Snell's law, what you will write? Mu glass for this, for the first interface, for the first refraction, mu glass into sine I is equal to mu water, that is 4/3 into sine into let's say mu water, I'll write, no issues. Mu water is given to be 4/3. I'll take it. Mu water into, what is the angle of refraction? Considered sine R. Correct. Now for the second interface, for the second refraction case, if you look into the figure, this is the incident ray and this is the angle of incidence. So applying the Snell, so I'll write mu water into sine of incident, angle of incidence, that is sine of R, is equal to mu air into sine of angle of escape. Correct? Okay, that makes this. Why? Because mu g into sine I and mu water into sine R and mu water into sine R, they are the common in the two equations. So that's why A is equal to B and B is equal to C. So what I can write is A is equal to B is equal to C, right? Because the interfaces are parallel, we can apply this. Correct? What is being asked? You are supposed to get the value of mu of glass in terms of I. Correct? So what I can write, I can take from there, this equals this. I can leave the middle term and I can put C. If A is equal to B is equal to C, I can use A is equal to C, right? So from there, what I can write is mu g sine I is equal to mu air into sine E. Now you just have to put the values. The value of mu g multiplied by sine I is equal to mu air. What is mu air? 1 into sine E. Now E is 90 degree in this case, correct? So sine 90. Here it becomes mu g is equal to 1 upon sine I. Simple. So the answer to this problem will be, in terms of the angle I, the refractive index of the medium glass will be given as 1 upon sine I. Let's look into the answer. 1 upon sine I, that's the correct answer. Let's look into the options. Option A will be the correct option in this case.